So in this video, we're going to summarize what we know about projectile motion and then derive the range equation from that knowledge. So let's start out by just making a quick sketch of a projectile in an xy coordinate system. So this direction is x, this direction is y. The projectile is launched at some initial angle to the horizontal, theta, and we call that vector v naught or v initial. Of course, we can think of it as two component vectors, Vx initial and Vy initial. And we know that as time goes on, Vx initial will continue to be constant, so Vx at all time equal Vx initial, provided that no additional forces like air resistance or wind is acting in the x-axis. And meanwhile, in the y direction, we can state that Vy, the y component of the velocity at any time, is equal to the initial y component of its velocity minus gt, where g is our acceleration due to gravity, which is acting in the downward direction. So as time goes on, the object's speed changes linearly with time. Now from these equations, we can write down the object's position in the x-axis and in the y-axis as a function of time. So our position in the x-axis, we'll just simply call it x, as x is a function of t in fact, is Vx t. And similarly, y, position in the y direction, in the vertical plane, is going to be Vy naught t minus 1/2 gt squared. So you can either think of this as the kinematic formula that we derived before, or you can think about it in terms of integrating the equation at the top to get the equation underneath. If we integrate with respect to time, we get from gt, we get 1/2 gt squared, and from Vy naught, we get Vy naught t. Now we're implicitly assuming that the motion starts at the origin, so we don't have to add any constant of integration because we know where we start the motion. Okay, so that describes our trajectory, and we could happily plot this as a parametric curve. At each time t, we can calculate x, we can calculate y, and plot the curve out. But maybe you want to plot the trajectory in terms of xy, so we can do that. We can combine x and y by eliminating t. Now how can we do that? Well, let's take this equation here and rearrange it to be t equals x over v of x, the x component of the velocity. Therefore, we can substitute this equation here, t, into our equation for the y position and end up with an expression for the coordinates of the trajectory throughout its flight. So this will simply be Vy naught times t. T, of course, is now x over Vx minus 1/2 gt squared, but t is now x over Vx, so it's x squared over Vx squared. And this equation here is the trajectory equation, and it has, as you might notice, the form of a parabola because it has an x term and an x squared term, and so the coefficients would be this collection of terms here, Vy over Vx, and the coefficient for the x squared term will be 1/2 g over Vx squared. So we can go a step further and find the range. So we're going to derive something called the range equation. So to derive the range equation, let's imagine sketching out the rest of the trajectory. So the object goes up and comes down, it follows a parabola, and it lands over here. And we'll call that distance r. We'll say that when the projectile has reached all the way to there, it's reached distance r, and at r, x equal r, y equals 0. Now this turns out to be very useful because it means that we can take this equation we wrote here and set y equal to 0, set x equal to r, and then solve. And because the constant term is going to be set to 0, this equation can be solved without resorting to plotting techniques or quadratic formulas or anything else. So let's now just rewrite this equation for the trajectory of the projectile for the specific case of where it ends up at x equal r. So at that position, y equals 0. So at y equals 0, x equal r, let's put all of this material in. So now we have 0 equals Vy initial over Vx minus 1/2 g x squared over Vx squared. So we can rearrange this. So now we've got 1/2 g x squared over Vx squared equal Vy initial x over Vx. At this point we notice a lot of terms will cancel, so this Vx here will cancel with this Vx squared, this x squared here cancels with this, and we're left with x equal Vy naught Vx naught times 2 all over g. And so now if we just make this replacement here of x equal r, this tells us that the range of our projectile is 2 Vy naught Vx naught over g. And let's see, I guess there's one final step we could make, because we actually know something about the initial x component and the initial y component. If we just reacquaint ourselves with those facts, remember that Vx naught equals V cosine theta, V naught cosine theta, and that Vy naught equals V naught sine theta. So if we use those pieces of information as well, we can put all of this together and end up with r equals 2 V naught cos theta, V naught sine theta over g, or r equals 2 V naught squared cos theta sine theta over g. And that, finally, is the range equation, and we'll stop there.